Hello AP Chemers. We are continuing our discussion of buffers, and we are using the Henderson-Hasselbach equation, which is kind of a shortcut for some calculations that we've seen already. So let's real quick derive the Henderson-Hasselbach equation just so you know where it comes from, but you no longer need to know how to derive it. That was something that was asked on the AP exam. It's no longer on the AP exam, the manipulation to get it. So real quick, just so you know, let's say I have a weak acid, HA, partially dissociates into H plus and A minus. So I write my K expression, concentration of the H plus times the A minus over the concentration of the acid. Now the A minus, that's my conjugate base. So I'm going to write conjugate base for A minus here. And HA is my acid, so I'm going to write acid here. If I rearrange this so I can get the H plus concentration by itself, the H plus concentration would be the Ka times the concentration of the acid over the concentration of the conjugate base, which is this equation right here. Now, if I take the negative log of all of these, on this side, negative log of H plus would be pH. Negative log of the Ka would be pKa. So remember, P just means negative log. And then negative log of this would be minus log of the acid over the conjugate base. To change that to plus, you would flip these. So it's pKa plus the log of the conjugate base over the acid concentration is equal to the pH. This is the Henderson-Hasselbach. So right here, again, this is the Henderson-Hasselbach equation for a weak acid and its salt. So if I have a buffer made of a weak acid with its conjugate, this is how I would calculate the pH for that buffer. So it's much easier than doing an ice chart. If I had a buffer that was made of a weak base and its conjugate acid or its salt, then I could similarly use this one. So this is the same thing as this one. This is for an acid. This one's for a base. So you'll notice instead of pH, it's POH. Instead of pKa, it's pKb. Instead of the conjugate base over the acid, it's the conjugate acid over the base. And again, just so you know, pKa or pKb will be negative log of the Ka or negative log of the Kb. So P just means negative log. It's a type of function. So let's try a problem where we can use the Henderson-Hasselbach equation to see how you can do it. So we're going to dissolve 2 grams of benzoic acid and 2 grams of sodium benzoate. So it's a weak acid and it's salt to make a buffer. And enough water to make a 1 liter solution. We want to calculate the pH using the Henderson-Hasselbach equation. So we're going to start out by writing our dissociation equations here. And so my salt, I'm going to start with that, and I'm going to call it just, sodium benzoate, I'm going to call it Na-benz, just for short. If you want to write out your formula, you can totally do that. So that dissociates fully into sodium ion and the benzoate ion. I'm also going to write my acid dissociation equation. So my benzoic acid, I'm going to call that H-benz. That partially dissociates into H plus and the benzoate ion. And remember, that's my common ion here. That's how I make a buffer using my benzoic acid and some of the benzoate there. Now I'm given grams, so I'm going to go ahead and convert to moles and then to molarity. So I'll do that on the side here. If I have 2.0 grams of my sodium benzoate, 1 mole of sodium benzoate, if you add them up, it's 144 grams. and then I'm going to divide by a liter. That's going to give me 0.0139 molar of the sodium benzoate. I also have 2.0 grams of the benzoic acid. I'm going to call that H-benz. 1 mole of that is 122.1 grams. And again, I'll divide by a liter. That gives me 0.0164 molar of the benzoic acid. So, if I wanted to calculate the pH of this, I have two options. I can do an ice chart for my benzoic acid. Start with my initial molarities, say that this is 0, do minus x plus x plus x, and plug in the Ka value, or I could use the Henderson-Hasselbach. So I'm going to choose to use the Henderson-Hasselbach here. So the Henderson-Hasselbach would be pH is equal to pKa plus the log of the conjugate base over the acid concentrations. So my pH is going to be pKa, remember, is negative log of the Ka, so negative log of, then you look up the Ka value for benzoic acid, it's 6.3 times 10 to the negative fifth, plus log of the concentration of my conjugate base. So my conjugate base is my sodium benzoate, so that's 0.0139 molar, divided by my benzoic acid. My acid is 0.0164. You punch that into your calculator and you get 4.13. So much simpler and easier than doing an ice chart. Takes a lot less time. So it's kind of nice. Let's try another one. So this one, I'm going to use my buffer above, the benzoic acid and the sodium benzoate, and now I'm going to add some NaOH to it. So remember, what we would do is we would figure out how many moles of each of my substances I start with, what the changes at the end, what I would get, and then I would do an ice chart. So we're going to do similar steps, except at the end we're not going to do an ice chart. We're going to use the Henderson-Hasselbach here. So first step is you want to decide what in your buffer is going to react with your added NaOH. So, there's my beaker. I have some H-benz, and I have some sodium benzoate. And I'm going to that add some NaOH, which has hydroxide ions. First, I decide what reacts with what. And so hydroxide is a base, so it's going to react with an acid. The acidic portion of this buffer would be the H-benz. So those two are going to react together. So I'm going to write out the equation for the reaction here. So the OH minus is going to react with my benzoic acid. And the product would be benzoate ion plus water. My OH minus will accept a proton from the benzoic acid to become water, and then the benzoic acid is left as the benzoate ion there. So I'm going to write out my initial change and my end result after my reaction. And you can do this with moles or with molarity. If you do it with moles, then make sure you change it to molarity at the end. If you start out by molarities in there, then you don't have to change it then. So it's totally up to you. So I need to figure out that 0.40 grams, what molarity that would be. So I'm going to change that on the side here. I have 0.40 grams of NaOH. 1 mole is 40 grams. So 0.01 moles of NaOH divided by 1 liter, it ends up being 0.01 molar NaOH. And I know that it's a 1-to-1 ratio for the NaOH, and so if 5.01 molar of NaOH, then I really have 0.01 molar of the OH minus. So that's what I'll use for my ice chart, 0.01 molar. My benzoic acid I know is 0.0164 molar from the above calculation. My benzoate is 0.0139 molar. And so what I do is I check which one's my limiting reactant. So it looks like I have less of my hydroxide, so that's my limiting reactant, so it's going to get used up. So this one is going to be minus 0.01 molar, minus 0.01 molar, and plus 0.01 molar. So at the end, this is going to be 0. This is going to be 0.0064 molar, and this is 0.0239 molar. Once I have my concentrations after the reaction, then normally what I would do is I would write the dissociation equation for my acid, for my benzoic acid, and then do an ice chart. But to make that a little bit easier, instead of doing that, I'm going to use the Henderson-Hasselbach. Of course, on the test or on the AP exam, it's totally up to you whether you want to do an ice chart or if you just want to use the Henderson-Hasselbach. So the Henderson-Hasselbach says pH is equal to pKa plus log of the conjugate base over the acid concentrations. So that's what I'm going to use. pH is going to be pKa, which is the negative log of the Ka. My Ka, it's still benzoic acid, so it's still 6.3 times 10 to the negative fifth, plus log of my conjugate base. So my conjugate base is the benzoate ion, so it's 0.0239, divided by my acid is 0.0064. Punch that in, you get 4.77. And that's my answer. So my buffer went from 4.13 when I added a bunch of sodium hydroxide. I got 4.77, so it did increase a little bit, which, would probably be expected. Now, it is a buffer, and so it's supposed to hold the pH constant. Well, each buffer has a buffering capacity. It's the amount of protons, H pluses, or hydroxide ions that buffer is able to handle in order to eliminate any extra H pluses or OH minuses so that your pH remains the same. Now, the way that a buffer works here is that, if you have a buffer, it has an acidic portion and a basic portion. So if you put in hydroxides, it reacts with the acidic portion like we see here. It eliminates all the base that you're adding, and it uses up some of your acidic portion and forms, some of the basic portion, So you still have the same kind of solution. Still, at the end, you have some benzoic acid and some sodium benzoate, just the molarities are slightly different, and so it keeps the pH about the same. Now, if I were to add an acid, then it would have reacted with the sodium benzoate, used up a little bit of it, used up all my H pluses, and it would have formed a little bit more of H bens. And so, again, I would get the same species in my solution, just, a little bit different molarities. And so it uses up the H pluses or the OH minuses that I give it because the buffer has a portion that's acidic and a portion that's basic to start with. And so you eliminate any extra H pluses or any OH minuses that you're adding, and therefore the pH and the pOH remain the same. But this only works to some extent. If I were to keep adding hydroxide to this, at some point, this is not going to be my limiting reactant. If I add enough of this that it was an excess, and this was my limiting reactant, then I've reached my buffering capacity. What will happen is that this would get used up, and I just have extra OH minuses. Once I have extra OH minuses, that changes my hydroxide ion concentration and my H plus concentration, and therefore the pH or the pOH change. And so the buffering capacity depends on the molarities of your buffer system, so the molarity of your weak acid and its conjugate, or it's your weak base and its conjugate. So the molarities have a factor, and also the strength of your buffer has to do with your Kas and your Kbs as well. So let's look at two different buffers and how their buffering capacities are different. So in this problem, I have two buffers. Both of them are the same substances. I have acetic acid and sodium acetate. One of the buffers, I have 5 molar of each. The other buffer, I have 0.05 molar of each. So this one's 10 times the concentration of that one. But both the acidic and basic portions are the same concentration. So first, I'm going to start by finding the original pH of just my buffer. So let me do that. So the way that you would do that is you would write out your equations. The dissociation of the sodium acetate and the dissociation of your acetic acid. So I'll do that maybe here. So my sodium acetate is NaCH3COO. That fully dissociates into Na plus and the acetate ion. And then I have my acetic acid, CH3COOH. That dissociates partially to give H plus and the acetate. Alright. And if I want the pH of this buffer, I have two options. I could either do an ice chart for my acid dissociation here, find, plug it into the K expression, find my X and all that stuff, or I could use the Henderson-Hasselbach. So I'm going to go ahead and use the Henderson-Hasselbach. So for the first buffer, I'm going to say pH is equal to the pKa. pKa is negative log of the Ka, which probably by now you know what the Ka for acetic acid is 1.8 times 10 to the negative fifth, plus log of my conjugate base, which is in this case the sodium acetate, it's 5.0 molar, over the concentration of the acid, which is the acetic acid. It is also 5.0 molar. So take a look at this. These two concentrations are the same, so 5 over 5 is equal to 1. What is log of 1? It's 0. When my conjugate base and my acid are the same concentration, turns out that the pH is going to be equal to the pKa. So the pH is just negative log of the Ka here, which in this case ends up being 4.74. Okay, let's do it for buffer B. So the pH is negative log of the Ka, or pKa, so it's still acetic acid and sodium acetate, so the same Ka, plus log of my conjugate base, which is the sodium acetate. It's now 0.05 molar, and my acetic acid is 0.05 molar. What happens to the pH? It's the same. 4.74 is my pH again, because it doesn't matter what the concentrations are, as long as they're the same concentration. Then when you divide them by each other, the acid and the conjugate base, it's equal to 1. Log of 1 is 0, and so the pH is equal to the pKa. So whenever you have a buffer and you have an acid and its conjugate, or a base and its conjugate, but they're both the same concentration, the pH will always be equal to the pKa, or the pOH will be equal to the pKb. All right, now what I'm going to do next is I'm going to add 0.01 moles of HCl. And I'm going to add that to a liter of my buffer. And I'm going to decide what happens to the pH. So in order to do that, first, you have to decide what reacts with what. So I like to draw my little beaker. So my beaker here, I have my acetic acid, CH3COOH. I have my sodium acetate, NaCH3COO. And I'm going to add some HCl, so that's really H pluses, so I'm putting in some H pluses. What's going to react? Well, H plus is an acid, so it's going to react with the basic portion of it, which is this. And I wrote sodium acetate. I probably should have just written acetate ion, so I'm going to cross out the Na there and put the negative here. You know, if you want to put your sodium, you can. It doesn't really matter. It's a spectator ion. So I'm going to start by writing my reaction that happens. So for both A and B, your H plus is going to react with the acetate ion. And guess what product you form? You form acetic acid. I'm going to write this twice. One time for A, one time for B. Because even though it's the same reaction, my numbers are different. Because my concentrations are different. So, let's see. My H plus looks like I'm adding 0.01 moles in a liter, so that's 0.01 molar. And that's for both of them, for both buffers. I'm adding 0.01 molar of the H plus or the HCl. For my first buffer in A, my concentrations of the acetic acid and the acetate are both 5 molar. So this is going to be 5.0 molar, and this is 5.0 molar. For B, both of them are 0.05 molar. All right, let's start with A. So looking at these, which one's my limiting reactant? Looks like I have a lot less of this one, so that's my limiting reactant. So that's how much is used up. So minus 0.01 molar, minus 0.01 molar, plus 0.01 molar. And so this at the end, I end up with 0 H pluses. I have 4.99 molar of this one, and I have 5.01 molar of that one. So if I want to find the pH, I'm going to use the Henderson Hasselbach. It's pKa plus log of the concentration of the conjugate base over the acid. And so for A, I am going to say pH is equal to negative log of the Ka, which is 1.8 times 10 to the negative fifth, plus log of my conjugate base, in this case is my acetate is 4.99, my acid is acetic acid 5.01. Calculate that, I end up with 4.74. Okay, I'm going to do the other one. I'm going to do it in blue here. So, I said that I have 0.01 moles of my H pluses, 0.05 molar of both of these. Let's compare these. Which one's my limiting reactant? Still the H plus. And so, minus 0.01 molar minus 0.01 molar plus 0.01 molar. So at the end of this reaction, I end up with 0 H pluses, and then 0.04 molar and 0.06 molar. So to find the pH, I'm going to use the Henderson Hasselbach. And again, if you want to use an ice chart, you're more than welcome to do that. Just the Henderson Hasselbach is a little bit easier. So pKa, which is negative log of the Ka, plus log of my conjugate base is 0.04 molar. My acid is 0.06 molar. And so if you calculate that, you end up with 4.55. My initial question was asking what change in pH happens when you add that 0.01 moles of HCl to these two buffers. And so looks like if I add my acid to my first buffer, pH remains the same. It was 4.74 initially. Let me move it down a little bit. So my first buffer in A was 4.74 initially, remained as 4.74. My second buffer started out as 4.74, went down slightly, 4.55. Not a significant difference. A significant difference would be probably a change of a pH of 1. So it's not significant, but it definitely changed. So both have good buffering capacity for my amount of acid, but which one has a better buffering capacity? Well, obviously it's A. So let's take a look at the differences between A and B. Well, A had a lot more stuff in it, a lot more buffer in it. It's 5 molar compared to B was, 0.05 molar. So definitely a big difference there. Alright, so we looked at the calculations with the buffers. Next, let's say I want to make a buffer. How would I go about making a buffer? Let's say, I need to hold a system at a certain pH. How would I do that? Your body has a lot of buffers. Your blood, for example, has a lot of buffers in it, like the bicarbonate ion, for example, in your blood system to keep your body from changing pH so much. So, two things that you need to consider here. It has to have enough stuff to resist changes to pH based on how much acid you're adding or how much base you're adding. And you need to pick a pH that would hold it at the desired pH. So, if your blood is slightly basic, I think it's like 7.2 to 7.4 or something like that is its pH, slightly basic. You want to have a buffer that is slightly basic, that is going to hold the pH at that level, not, something that's way higher or way lower. So, let's say I want to make a buffer that will maintain the pH as 4.3, which means that I want my H plus concentration to be 10 to the negative 4.3, which ends up being as 5 times 10 to the negative fifth. So I would want to pick a buffer that's acidic because, that's an acidic pH. So I want to pick a buffer that is an acid with its conjugate base. So a weak acid and its salt, as opposed to a weak base and its salt, since this is acidic. And I want to pick my weak acid to have a Ka value that's something times 10 to the negative fifth. You want your weak acid in your buffer to have the same Ka value as close to the Ka value as your H plus concentration that's desired. So let's actually do a problem So this one says, how would you prepare a buffer that's made of acetic acid and sodium acetate that will hold your pH at 5.00? So let's try to think about this. I know that I'm going to use acetic acid and sodium acetate. And I know that my Ka expression is going to be the concentration of the H plus times A minus over HA. Or, if I'm using acetic acid and sodium acetate, let me rewrite that. I want it to say H plus times the A minus, in this case would be the acetate ion. The HA would be your actual acid, acetic acid. All right, well, what do I know from here? Well, I know the Ka of acetic acid, right? I can plug that in. I also know what I want my H plus concentration to be because I know what the pH is. So I know that the pH should be 5.00, which tells me that I want my H plus concentration to be 10 to the negative 5.00. So, same thing as 1.0 times 10 to the negative fifth molar. So I know my Ka value. So I'm going to go ahead and plug that in, 1.8 times 10 to the negative fifth. And I also know my H plus concentration. I want it to be 1.0 times 10 to the negative fifth. And my acetate ion concentration goes here. My acetic acid concentration goes there. If you were to move this value to the other side, it would go in the denominator, right? So let's rewrite that. That would be 1.8 times 10 to the negative fifth over 1.0 times 10 to the negative fifth is equal to the concentration of the acetate over the concentration of the acetic acid. If you divide that, that ends up being 1.8, right? Which is the same thing as like 1.8 over 1. What is that telling you? That's telling me that I want to make this buffer so that my acetate ion concentration would be 1.8 times the concentration of my acetic acid. It doesn't matter how much I use. It doesn't matter what the volume is. As long as the acetate ion concentration is 1.8 times the concentration of my CH3COOH, that's fine. So if I, for example, make the acetic acid 1 molar, then the acetate ion would be 1.8 molar. So if I say that I want to make 1 liter of my solution, what I would use is I would figure out what 1.8 moles of the sodium acetate is, and I would use 1 mole of the acetic acid. If I mix those together in a 1 liter volumetric flask, I should get a pH of 5.00. Let's try another one. So this problem says how much KOH must be added to a 1 liter of 2 molar acetic acid to make a buffer with a pH of 5. Now, it's a hard question. It's hard to figure out what to do first, but there should be something that's really bothering you about this question. When I first read this question, it really bothers me because it's telling me, it's asking how much potassium hydroxide I'm adding to acetic acid to make a buffer with a pH of 5. What's a buffer? A buffer is a weak acid and its conjugate, or a weak base and its conjugate, right? So I have a weak acid here, but I don't have its conjugate anywhere. I have acetic acid, but nowhere do I have acetate. If I have acetic acid and I want to make a buffer, I need some acetate there. Potassium acetate, sodium acetate, lithium acetate, anything with acetate to make it into a buffer. And so there's no buffer. How can I make a buffer if I don't have, my conjugate there? Well, you can. You just gotta wait a little bit and see what's gonna happen. So, right now, I don't have a buffer. All I have is KOH and acetic acid. I'm gonna mix them together to figure out how much KOH I need to add, right? Well, let's write the reaction that's going to happen. In chemistry, whenever they're talking about a reaction, you're mixing two things together, write the equation first. So my KOH, I don't care about my potassium. It's a spectator. It's OH minus that's reacting here. I'm going to mix that with my acetic acid. And what would I form? Well, this is a base. This is an acid. A base is a proton acceptor, so it's going to grab an H plus from the acetic acid to form water. And then the acetic acid is going to donate an H plus to form acetate ion. So I'm going to form water and acetate ion. And once I do that, look at that. Now, if you have some left over of this, and some of this formed, I would have made a buffer. Isn't that cool? I thought that was really cool when I first looked at this problem. So anyway, what am I asked for? I'm asked for how much of my KOH I'm adding. So really how much of the OH minus I need to add. So since I don't know how much I need, let's call that X. Okay. I know how much acetic acid I have. I have 2 molar. So I'm going to write 2 molar here. I don't care about my water. My acetate to start with is 0 because I didn't start with any acetate. I just started with my acetic acid and my potassium hydroxide. Well, what's going to be my limiting reactant? If I'm asked how much KOH I need to add to this, then that means I need to use up all my KOH, right? I should not have extra OH minuses floating around. So if I start out with X here, X is going to get used up. So I end up with a little bit of this and a little bit of this so I can make a buffer. So I'm going to say my change is X. So minus X plus X. So at the end of this reaction, I don't have any leftover hydroxides. I have 2 minus X of this and X of this. So you can use your Ka expression if you would like, or you can even use the Henderson Hasselbach if you want. It's totally up to you. I'll use my Ka expression. Ka is the concentration of the Ka for acetic acid is the concentration of the H plus times concentration of the acetate over the acetic acid. My Ka is 1.8 times 10 to the negative fifth. That's not going to change for my acetic acid unless you change the temperature, which we're not. My H plus, I know I want my pH to be 5, so that means that my H plus concentration needs to be 10 to the negative fifth, which is 1.0 times 10 to the negative fifth molar, basically. So that's my H plus 1.0 times 10 to the negative fifth. And then my acetate needs to be X. My acetic acid needs to be 2 minus X. Look at that. You can solve for X. This is just basic algebra. You don't need a quadratic for this or, the intersection or anything like that. This is just basic algebra. If you solve for X, that ends up being 1.29 molar. And so that should be my starting concentration of my hydroxide, which is my starting concentration of my KOH, because everything's a 1-to-1-to-1 ratio. And so 1.29 moles per liter of the KOH. I'm going to change that to grams. 56.1 grams, I believe, is the molar mass. And my buffer is 1 liter, 0.00 liters. And so that ends up being 72.4 grams of KOH.